to be here to speak to you about Cauchy, Bien-Aimé, Galton-Watson, and Bertoin. And first, I'd like to tell you how I met Jean. It was in this cozy amphitheater of the École Normale Supérieure of Paris, not that far from here. And actually, Jean taught the first probability class I had at École Normale Supérieure. At that moment, there were no probability taught in class préparatoire. And this course was integration, measure theory, and then probability. So we learned the measure theory before learning discrete probability. It was nice. And actually, Jean's lectures, together with Mathilde Veil's tutorials, was really one of the main things that made my choice to do probability theory. And it was a bit like Gregory explained. The lecture was very clear, very precise, yet profound and beautiful. It was really amazing. And also, one day, we asked Jean to make a little surprise to one of the students of our class called Jeanne. So Jean went on stage and he said, before beginning today's lecture, Jeanne, I would like to wish you a very happy birthday. And today, I'm very happy to say, Jean, I wish you a very happy birthday. The outline of my talk is first some introduction, motivation, pictures, and so on. Then nothing, a theorem, and then a proof. So let's start with the motivation. The global context is to understand the geometry of random trees. Here I will be a bit vague. Later I will be vague as well. But in this talk, for me, a tree will be a plane tree. A tree drawn in the plane with a root, an ancestor, and it is a plane in the sense that every vertex has children which are ordered. There is a notion of order between the vertices. So as plane trees, these trees are different. And we consider a Galton-Watson tree, a Bien-Aimé Galton-Watson tree, a Bien-Aimé tree, a Galton-Watson tree, condition having n vertices with offspring distribution mu. Mu is the main parameter of the model. Mu of k is the probability of having k children. It's really the simplest geometrical model you can imagine. You start from one ancestor, which has a random number of children with law mu, and so on. Its children have a random number of children. Everything is IID, the simplest geometrical model which is possible. And you condition it on having n vertices. So I assume that all the conditionings are non-degenerate. And the global, maybe vague question is, what does this look like as n goes to infinity? I will be a bit more precise in what sense we mean look like. Okay. And there are several motivations to addressing this question, coming from applications in different fields, computer science, network theory, complexity, in biology, of course, phylogenetic trees, in statistical physics. But also as a mathematical model, it's a very, we can say, simple model to define, yet it has a very rich probabilistic structure with very nice different tools coming from different fields to tackle the understanding of this large-scale geometry. What happens? I don't know. And some examples, some specific examples. If you take a geometric offspring distribution, then the tree condition having n vertices just follows the uniform distribution on the set of all plane trees with n vertices. It's not very difficult to check. If you take this other probability distribution, you get the uniform distribution on the set of all binary trees with n vertices. And okay, so this is the, I think, not the last version, so there are typos. So your exercise is to find all the typos. Okay, here it's okay, it's still true, but okay, you can take, let's take lambda equal 1. You take a Poisson distribution, and you take your tree Tn, which is a Poisson 1 Galton-Watson tree condition having n vertices. You label the vertices uniformly, and what you get is a Kelly tree, a uniform labeled tree with n vertices. So if you understand the general model of Bjarne-Galton-Watson tree with offspring distribution mu, you can understand all these models at the same time. Here is a simulation of a large uniform plane tree with 15,000 vertices for one particular offspring distribution. So it seems a bit, what does it look like? Yeah, the Brownian tree, but I know. And now I will explain an overview of known results concerning limits of large trees in two directions: local limits, scaling limits. In the local limit framework, you sit at the ancestor and you look at what happens at a finite neighborhood around the root. And we will consider two regimes. The first regime is the critical regime, where the mean number of children is 1, exactly 1. And the subcritical regime, where the mean number of children is less than 1, and we impose an additional condition that the radius of convergence of the generating series of the offspring distribution is exactly rho mu, which is less than 1. Okay, sorry. Typo. What should be here? Yeah, equal 1. Okay, of course, for z equal 1, you get some of the mu i's, which is 1. So here, the radius of convergence is exactly 1. We do not want it to be greater than 1. Okay, so this prevents from having, for example, exponential tails. Okay. And it turns out that these two regimes, critical, subcritical, cover all the cases. Why? Because there is a nice exponential tilting technique which allows you to tilt an offspring distribution mu when possible with a parameter c. And of course, you get another offspring distribution, but when conditioned having n vertices, these two offspring distributions give you the same distribution on trees with n vertices. So by playing on this parameter c, the supercritical case essentially boils down to one of these two cases. And the really nice feature is that in the case of local limits, we always have local limits, as I will explain now. First case, critical. Critical case, no additional assumptions. You take a Galton-Watson tree with n vertices, and it turns out that we have a limit in the local sense. So I will explain what this convergence means in just a second. But before that, I would like to tell you that the limit is a locally finite tree with an infinite spine, the so-called Bjarne-Galton-Watson tree conditioned to survive. You have an infinite spine. Grafted on it, you have independent random trees. I will not explain precisely the construction, but you have an infinite spine like that. And this convergence is in distribution for the local distance, which roughly speaking just means that if you cut your trees at a fixed height, you look at a finite neighborhood around your ancestor, you have convergence in distribution. Okay, so this is convergence in distribution for random variables taking values in a countable set. So not very. So in the critical case, no additional assumptions, you always have a local limit. And this is nice. Of course, it's always nice to have a limiting object, a limit theorem, but it can also give you statistics of combinatorial flavor concerning your trees by evaluating, by looking this convergence through the lens of continuous functionals with respect to the local topology, such as the degree of the root or the length of the leftmost path. However, there are some nice statistics which we could be interested in, such as the maximal degree, which are not continuous with respect to the local topology. So if you want to study the maximal degrees in trees, the local topology is not adapted. And this is the critical case. Now, subcritical case. Here, you should assume equal to 1, sorry. And we also have a limit theorem convergence in distribution for the local topology to a limit object. But now it has a finite spine. Its length follows a geometric distribution. And on the top of the spine, you graphed infinitely many trees. So here, this limiting tree is not locally finite anymore. So you have to modify a bit the notion of cutting, but I don't want to enter details. Here, roughly speaking, you're intuitively maybe mu is subcritical, but you force it to have n children. You force it to be large. And from the local point of view, what you see is a condensation, sort of condensation. You have a vertex of a maximal degree in the local limit. A condensation, I think the name was coined by Johnson and Stephenson. Again, in the local limit framework, you always have limits. So rather spectacular. In all the cases, you have local limits. Now, scaling limits, there will be again two regimes: critical regime and subcritical regime. But to understand the global geometry of the tree, for scaling limits, we will need additional regularity assumptions, which will appear very soon. And to define precisely in what sense we are considering scaling limits of random trees, there are different ways of doing it. You can view trees as graphs and view graphs as compact metric spaces and work with a Gromov-Hausdorff topology. To do that, you can code, for example, your trees with the contour function and stuff like that. But I will not do that here. I will code the Lukasiewicz, I will use the coding by the Lukasiewicz path, because one of the main objects of interest for me in this talk will be the maximal degree. And we'll see that the Lukasiewicz path encodes in a very easy way maximal degrees in trees. So what is the Lukasiewicz path? You go through the tree by using the depth first search. And each time you see a new vertex, you make a jump of size, the number of children minus 1. So for example, here at the root, you see 2 children. So you make a jump of size 1. Then you go to the next vertex, it has 4 children. So you make a jump of size 3. A vertex of size 2, a vertex 2, which has 0 children, so a jump size minus 1. 3 has 2 children, so you make a jump of size 1. Okay, 4 has 0 children, jump of size minus 1. Okay, and you continue like that. And at the end, you get a path which makes negative jumps of amplitude at most minus 1. It finishes at minus 1 at the last time. And this is not a coincidence, it's always the case. And this gives you a bijective encoding of trees, plane trees, by so-called downward skip-free walks. And since jumps correspond to number of children, the maximal out degree, maximal number of children, is just the maximal jump of W of t. Here there is a typo. You have to add 1 because here jumps are number of children minus 1. So this forces you not to sleep because there are typos everywhere. So now assume mu is critical, and first subcase, finite variance. Then essentially Aldous showed that if you scale your Lukasiewicz path in time by n, which is the number of vertices, and in space by a square root of n, which is of course reminiscent of the central limit theorem, in the limit you get the Brownian excursion. And here I make a linear interpolation of the Lukasiewicz path. So you have a big tree, it's Lukasiewicz path. You could write limit theorems for the contour function, but I won't do it here. I won't need that. And the consequence of this is, as I said, we will be really interested in maximal degrees. Since the Brownian excursion is continuous, well, it's not an immediate corollary of this, but it essentially boils down to that. Since the Brownian excursion is continuous, the maximal degree of your tree is little o of square root n in probability. Depending on some models, you could be more precise, but in general, there is no universal limit theorem for the maximal degree in this case, because if you take, for example, binary trees, the maximal out degree will be 2. If you take plane trees or Cayley trees, you will get different behaviors. Okay, now assume that mu is critical and has infinite variance. If we do that, we will treat all the critical cases. But to have scaling limits in the infinite variance case, here we need an additional regularity assumption, which is namely the fact that the offspring distribution belongs to the domain of attraction of an alpha stable distribution, which means essentially that the tail of mu is heavy. The tail of mu is some function L, which is slowly varying, divided by n to the power alpha. And a slowly varying function is defined here, okay? And if you don't like yet slowly varying functions, you can just imagine that L of n is asymptotic to some constant. It's a sequence which tends to a constant, or you can take log n or log n to some power log n. So for the moment, if you want, you can ignore the slowly varying function and replace this by asymptotic to constant over n to the power alpha. But we will see in a few minutes that there is no escape from slowly varying functions. Up, where was I? Okay, yes, no, no. Okay, and in this framework, critical offspring distribution, infinite variance, domain of attraction of a stable law, we have also a limit theorem for the Lukasiewicz path. But I drank too much coffee. And now here we do not do a linear interpolation anymore. We take a Cadlag sort of interpolation, and the scaling is not square root n anymore. It's n to the power 1 over alpha up to a slowly varying constant. And the limit is not continuous anymore. It's a normalized excursion of an alpha stable spectrally positive Levy process. Here is a simulation. It has jumps which correspond to nodes with a big degree you see on the left. And here we really get a limit theorem for the maximal degree. The maximal degree is of this order. What's happening? The maximal degree is of this order because this convergence in distribution is for the Skorokhod J1 topology for Cadlag processes, and the maximal jump is a continuous functional in this topology. So the maximal jump of the left-hand side will converge in distribution to the maximal jump of the right-hand side. So we get that the maximal degree is of this order, and more precisely, the maximal degree of Tn divided by this converges in distribution to the maximal jump of this nice excursion. And the second maximal degree as well, and so on. So all the maximal degrees are of this order. And observe that here alpha equal 1 is excluded. Now, what happens in the subcritical case? We assume that mu is subcritical. And here we make an assumption, a stronger assumption that in the previous case, we make an assumption on the local probability mu of n, not just on the tail of mu. And we assume that mu is of this form. So here there is a typo. Can you find it? Yeah, because if beta is less than 1, this thing will not have a finite expectation. So since we assume that mu is subcritical, we have to impose, well, at least to be really on safe grounds, that beta is greater than 1. So you should replace beta greater than 0 by beta greater than 1. And in this case, we have a limit theorem for the Lukasiewicz path. We look at the Lukasiewicz path, and we have a limit theorem. The Lukasiewicz path in this case looks like this. This is this deterministic function, which starts at 1 and goes down like this. And here the scaling is of order n, not like n to some power before. It means, essentially speaking, that you have in this subcritical tree, which you condition having n vertices, there will be one vertex with really, really huge degree of order 1 minus m times n, and all the other degrees will be smaller. So here, okay, since this there's a small issue in 0, so this is not 100% precise. So let's say 99% precise, but I put a lot of things under the rug. Yeah, so this is the picture of the Lukasiewicz path in this case. Intuitively speaking, you are subcritical, and under this regularity assumption, what costs the less when you condition to be large is to have a condensation, a one big jump principle. Okay, this is actually rather standard for sub-exponential distributions. And as I said, the consequence of this is that the maximal degree is of order 1 minus m times n, and the second maximal degree is little o of n in probability. There's really a one big jump principle. And you could say that this is intuitively consistent with the local limit, which, if you remember, is a random tree which has a finite spine, and on top of the spine, you had infinitely many trees grafted on it. So here you have, in the global picture, one vertex with maximal degree, which you could say becomes the vertex on the top of the spine of this tree. Okay. Now, our theorem, which it was a joint work with Loïc Richier. We considered a critical offspring distribution in the case alpha equal 1, meaning that we assume that the tail of mu, with a parenthesis, is of the form L of n over n, with L slowly varying. Okay, remember that for Thomas Duquesne's theorem, the case alpha equal 1 was excluded. Okay, so we make this assumption, and here observe that there is no escape at all from slowly varying functions. Because if you put here asymptotic to constant over n, you have infinite mean. Okay, so if you want to have finite mean, you really have to have slowly varying functions. And here we consider Bianet-Megalton-Watson tree condition having at least n vertices, not exactly n, but at least. I will comment on that afterwards. And so what does this look like? So here, come back. Here's a simulation for this particular offspring distribution. So you see something a bit like in between the picture of condensation and the stable case. So it's and I will make things a bit precise by stating limit theorems for this object in the next slide. Okay, so the hypothesis mu critical, domain of attraction of a Cauchy distribution. And with Loïc, we showed that we first have a limit theorem for the Lukasiewicz path. So maybe, do I have a picture? Yeah. So what does this look like? In the limit, you have a one big jump principle. You will have one big jump and then a linear drift. The main difference with the condensation case before is that here, the time interval is random, which comes from the fact that we condition the tree on having at least n vertices, and here we scale time by a factor n. So this is why here the time interval is random. Okay. But in the limit, you get a one big jump principle. In the limit, you will make a big jump at the origin and then drift linearly. And in space, the scaling is not n. It's not n to some power. It's n divided by a slowly varying function L1, which goes to infinity. So this is really a sort of really in between n and n to some power, which is less than 1. Here you have a slowly varying function. And the consequence of this, by looking at the maximal degree, is that the maximal degree of this thing, which is the maximal jump, well, you get that the maximal degree divided by n to the power, divided by n to some slowly varying function, has a limit. And the other degrees are little o of this sequence. And observe that since mu is critical, the local limit is Bjarne-Galton-Watson-Shree condition to survive, which has an infinite spine. So here the picture is not that consistent with the local limit, because we have condensation, we have one vertex of maximal degree, yet the local limit is a locally finite tree. And this is explained, of course, by the fact that the vertex with maximal degree escapes to infinity. So we can wonder, okay, how fast does it escape to infinity? This is the content of our second result. We look at the height of the vertex with maximal degree, and we show that it escapes to infinity as a slowly varying function. So it's not that, maybe not that high in the tree, yet it's still high. And we even get explicit limit with this, which is an exponential distribution of perimeter 1. And if we assume a stronger regularity assumption on mu, not only an assumption on the tail, but on the local probability, then we can get limit theorems for the tree condition having exactly n vertices. So this is maybe not, this is a bit in contrast with the case alpha between 1 and 2. In the case alpha greater than 1, you make an assumption on the tail and you get results on the tree condition having exactly n vertices. But in the case alpha equal 1, it seems that if you only make this tail assumption, it's not enough to get, in general, results for the tree condition having exactly n vertices. But if you make a local assumption, then you get limit theorems for local conditioning. And actually, even if this question is natural because the case alpha equal 1 was missing and you get really nice results, our initial motivation to consider this model actually comes from random maps, but I won't have time to go into that. Now, proof. So buckle your seatbelts. I will only give you the main steps of the proof of the one big jump principle, namely the fact that the Lukasiewicz path conveniently scaled converges to something like that. And the main ingredient is, as usual in this framework, is to use codings by random walks, which of course naturally appear because the number of children are independent and the Lukasiewicz path encodes the number of children. Of course, there is a conditioning which breaks all the independence, but in the shadows, there are still independents. Observe that, okay, so what is this random walk? It starts from 0, and the probability that it makes a jump of size I is mu of I plus 1. This is because if we see I children, we make a jump of size I minus 1. And since mu is critical, the walk is centered. We will consider the first time, maybe this I will. Right. I don't have the definition anyway. It's nice to be able to write on blackboards again. And it's not that easy. It's easy or not that difficult to check that the Lukasiewicz path of the tree condition having at least n vertices has the same law as the random walk, stopped at the first hitting time of -1, condition on the fact that this time does not occur before time n. This comes from really the model. Okay. Here is a simulation of the random walk W for the offspring distribution. I don't remember, what was it? I think it was something like that, I think. And here's a simulation of this random walk. Okay, so what do you see? You see something a bit strange. It seems that this random walk tends to go downwards. But remember, mu is critical, so the random walk is centered. So this seemingly paradox just comes from the fact that if you write the sort of the central limit, I hope there are no epileptics in the room. The reason you see this picture comes from the associated central limit theorem. We're in the domain of attraction of a stable law, so there are scaling constants, scaling sequences, such that we have a central limit theorem. So not central limit theorem in the sense that we are Gaussian. Here we are stable. So in the limit, we get a stable distribution, and more precisely a Cauchy distribution. Here asymmetric with skewness 1. And we have two scaling sequences. A centering sequence and how do you say? Space sequence. Yeah. This is really in contrast with the case alpha greater than 1. When alpha is greater than 1, you do not need a centering sequence. But here, it's because alpha is equal to 1 that you need this centering sequence. This Bn, roughly speaking, corresponds to this drift you see. So you seem to have a drift, even if there is no drift. This random walk is nonetheless recurrent. What will happen is that if you wait long enough, you will make a huge jump, which will bring you far above. But there's this sort of invisible drift, which pushes you downwards. And at what speed? Both sequences an and bn are of order n, but they are slowly varying functions. So an and bn go to infinity as n, but they are slowly varying functions, and bn grows in absolute value faster than an. Okay? And again, this is really why things will happen differently for alpha equal to 1, because of this centering sequence. Okay, this was the first ingredient, scaling sequences. I will also need weak record times, which are defined here. You start from 0 and you look at the times where you are at least equal to your current maximum. In this example, you have 4 weak record times up to time 8, and zeta, this one, is equal to -1, is equal to 1, sorry. Okay. Up, no. To get limit theorems for random trees, we start by getting that's okay, let's see if I for technical reasons, I think one should be at least, is it like that? I had a probability 1/2 of getting it right. Of course, you could put greater than, but we will see. So this is one of the two main inputs to show limit theorems for our trees. Okay, it connects probability, this probability first time you hit -1, first week record time, and when you multiply that, you get this as n goes to infinity. Okay, and how do you show that? Well, we get estimates with Loic on the tail of the first time you hit -1 and of the first week record time. So here really the tricky thing is that alpha is equal to 1, and we did not find in the literature such estimates for strong and weak record times in the Cauchy domain of attraction. And to show that, we just in 3 words, we use the Wieder-Hopf factorization, which connects these probabilities to local probabilities of being non-negative. And we can estimate these probabilities thanks to recent estimates of Quentin Berger, which wrote a very nice sort of survey article with a lot of different estimates for random walks in the Cauchy domain of attraction. And then we use results for regularly varying functions, and namely the Hans monotone density theorem. And once you get this and this, you multiply, this slowly varying function disappears. So this is a bit the miracle. In general, we do not know what this lambda is, but we just need to get the product. So this and this disappears. So, and we get L of absolute value of Bn divided by absolute value of Bn, which is exactly this. Okay? So this was the first ingredient, and the second ingredient will involve the last week record time up to time n. So what does that mean? Here n equal to 100,000, and you look up to time 100,000, the last week record time up to this time. So you have week record times here, 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 and here is the last week record time up to n. Okay, so it's a random variable which depends, which is a function of the random walk. Okay, so I remember it. Okay. Okay. This is consistent with the picture. In in this example is rather close to 0, and you can check it by using a scaling limit argument. If you want the equivalent of Donsker's theorem for this Cauchy random walk, and this comes from the fact that you have this sort of invisible drift, which will, in effect, has as consequence the fact that In will be very close to 0. We could be a bit more precise, but I don't want to enter these considerations. And second case, we can explicitly compute the law of In in terms of the tail of zeta n T1. And where does this come from? It's just a time reversal argument. This quantity comes from here, and this quantity comes from here. Okay. So these, again, are just results on Cauchy random walks. And we will, I think, just need these two results to get this one big jump principle on conditioned random walks. So let's prove the one big jump principle. What is the idea of the proof? So first, we define this Wn, which is the random walk conditioned on not touching -1 before time n. And we want to show that this Wn satisfies a one big jump principle. And the idea to do that is to change, change what? Glasses, change your brain, I don't know. So to introduce a completely different object, Zn, which is another random walk, not exactly random walk, but another path, random path, such that two things are true. The first one is that it satisfies a one big jump principle for free. And two, it's not that far from Wn in the total variation sense. Okay, and this is the main idea. We consider a new path Zn, which will satisfy one big jump principle, and we will show that in total variation, Zn and Wn are close. So since Zn satisfies the one big jump principle and is close to Wn, we get that Wn satisfies the one big jump principle. So what is this intricate definition of Zn? There are 4 steps. The first step is to sample a random variable according to In. So In, it's a random variable. You sample it. Okay. Sample. You sample it. Okay. Once it is sampled, you will do 3 things. You will complete what happens before In. You will make a jump, and then you will do something afterwards. So the first thing you do, conditionally giving In, is this. Then you do a jump, and then you okay, so let's do it again. Okay. Okay, so again, you sample In, and conditionally giving In, you have 3 independent pieces. This piece before In, what is it? It's just the random walk condition not to touch -1. Then you make a jump. What is the size of the jump? Well, you force the jump of being of size at least absolute value of Bn. So you force this one big jump to arrive, and then you continue your life as a random walk. So this is the definition of the modified path Zn. Of course, there is not independence because there is this In, but conditionally given In, you have independence of 3 pieces. Now the main theorem is this one. It says that in total variation, these 2 paths are not that far. And it's not difficult to check that the modified path satisfies the one big jump principle, a bit by construction. Okay, so let's prove this. So what is the idea? The idea to show that these 2 things are close in total variation is to find a good event of paths, Gn, such that for the modified walk, Gn is typical, meaning that the probability that the modified path is in the good event tends to 1, and such that when you restrict yourself to the good event, you are close in total variation. Okay, so here, of course, the difficulty is that to show directly that Wn lives with high probability in Gn is difficult. So this is why you go through this way. So let's build up the proof. So we will need a deterministic sequence Xn such that you have this, okay? Now, what is the good event. The good event is you stay non-negative up to time n, and before time xn, you make a jump, a unique jump of size at least absolute value of Bn. Okay, so this event is you have not exactly a one big jump principle, because maybe you could have maybe another jump of size absolute value of Bn over 2, stuff like that. But here you just impose that before time xn, you make only one jump of size at least absolute value of Bn. So it's not that restrictive, but still it's restricted enough to get what we want. Okay. Showing the fact that the modified path lives in this good event with probability tending to 1 is not that difficult. It comes essentially from the definition of the modified path. We did more or less everything that so that this is true. So now to show 2, to simplify a bit notation, I will not take all events A, but I will just fix a path W, a fixed one, in the good event, and show that this thing tends to 0 uniformly in W. So you should, okay, it's not exactly what we want, but okay, it will convey the main idea, and it will be technical, but not that technical. Okay, so let's go. This is the fixed path in the good event. So let's compute the probability that your conditioned random walk, which is conditioned on zeta at least equal to n, is equal to the fixed path W. So by definition, so here there is a typo. So now I have to wake up. What is happening? Yeah, there is no n here. Okay, n was for the conditioned walk, conditioned on zeta at least equal to n. So if you write it using okay, the definition, here there will be no n. This is just the probability that your random walk up to time n is equal to this path W divided by the probability that zeta is at least equal to n. 2 typos. Now let's compute the probability that the modified random walk is equal to this path W. And for free, you can impose that In is at most Xn. Why? Well, we want to show that this thing minus this thing without the In tends to 0. But since this tends to 0, you can add this event here. So now let's use the definition of the modified. Okay, so now you have a heart attack. This is the modified random walk. And so you use the definition, you write it like that. Why? Well, the modified random walk, how did you get it? You first sample In, and then you sample the first part before the jump. You sample the jump, and then what happens afterwards. So this is what happens before the jump. This is what happens at the jump. And this is what happens essentially after the jump. Okay, here there's another typo, but okay, I sweep it under the rug. And the miracle is that since we have introduced this good event where there is a unique jump before time xn, which is big, in this sum, there is only one element, which corresponds to the unique j between 1 and xn, such that in this path you took in the good event, the jump is at least absolute value of Bn. So in this sum, you see here, in this term will always be equal to 0, but not for this unique element j of W. So this huge sum boils down to just one term. Okay, which is this one. And again, here, there should not be n here. This is without the n, here's without the n. And now you recognize that this quantity is also here. So you have just to compare this thing in the denominator with this thing. This is where we will use results on random walks. Okay, we use this formula here to change this fraction in this fraction. And then you use this asymptotics to get precisely this. So here I'm putting things under the rug because J of W, you do not know exactly what it is, but it's at most xn, which is little o of n, so everything works. Okay. It was its punishment. Okay, and this completes the proof. So it may be, it seems maybe a bit technical, but the main idea is that you just from one estimate on probabilities, essentially the only thing you use really, which is rather involved, is just this estimate. And from this estimate on probabilities, you get really a global result controlling the total variation of a random path. So you get this probability, estimates on probability gives you leverage to get information on whole paths. And in this way, you get this one big jump principle. Okay. That's all. Thanks for your attention.
Thank you very much, Igor. I guess we'll have many questions for you. Jean-François Le Gall.
There was another typo.
Yes, it's not about typos, but there is one more. Yeah? No, I was wondering, in your research, you condition on the fact that the size of the tree is greater than n, and you said that you cannot get it for the size equal to n. Is this just a technical problem, or is there something deeper?
Yeah, I guess it's something deeper. It comes from the fact that for sub-exponential distributions, if you want to have local estimates, you really need to have information on local probabilities. It comes from the fact that the estimates we need are in sort of moderate deviation regimes, in contrast with the critical case domain of attraction, where we are in, we look at the window of the fluctuations. And in this case, because of this Bn, because of the centering constant, you need, you are in a sort of other window. So I think it's not just a technical condition. We don't have concrete examples of Ostrom distributions where we do not get the result, but I would guess that yeah, it's not just a technical assumption.
Yes, I have also a question about, so you have this one big jump principle, but then it seems that besides this first big jump, you have in fact many other big jumps of smaller scales. So can you study also, what would correspond maybe to a fluctuation result from this, let's say, law of large numbers that you get?
Yes, absolutely. And this is where also the fact that this approximation by Zn is useful, because Zn tells you that your path Wn really behaves like you do some stuff here, you make a one big jump, and then you evolve like an unconditioned random walk. Here, the size is little o of n. You will have jumps here, but they will be very small compared to the jumps you make here. And the jumps you make here, it's just the jumps on the time scale n of an unconditioned random walk. And for this random walk, you can write, maybe if I write yi, this random walk. I guess something like that. This will converge in distribution for the square code topology to a Cauchy process. And so the maximum, you have this big jump. The other next jumps, you read them here. So they correspond to the jumps of CT. And so what is the scale? It's the scale AN. So the maximal jump is here, is of order Bn. And the next jumps, there will be countably many of that order, will be of order An. At a smaller scale because as we have seen for scaling constants, An is little o of absolute value of Bn. So it's really a sort of, you have condensation, but the scale from the maximal jump to the second maximal jump, you just lose a slowly varying function. So it's, yeah. And intuitively speaking, what this tree looks like, you will have this sort of spine, which has a length, maybe log n or something like that. I mean, a slowly varying function. And on top, you graphed a lot of independent trees on it. So this is maybe a rough picture.
So in earlier results that you presented, when the tail of the reproduction law is regularly varying with index minus beta or something like this, the limit theorem that you obtain, in the limit theorem that you obtained, beta does not appear. So do you expect your result to hold under more general assumptions than regular variation?
Okay, let's try to find it. This one? Yeah. You mean the question is in the statement beta does not appear?
Yeah.
Okay, yeah. So it will appear if we look at the next jumps. When you look at the fluctuations, then it will appear. And so your question is?
Whether the theorem holds in under a more general assumption than having a tail which is regularly varying.
So I would say that a bit like this case, if you get an estimate on probabilities, then you get a one big jump principle. If you have a centered random walk, which satisfies this, so here, take a centered random walk, take C greater than 0, and assume that you have this. So this says that, okay, to be at time n very high, it means that you made only one jump of size Cn at one of the n values. So if you have this, you get the one big jump principle, a bit like this estimate entails control on the whole path. So this is known for so-called sub-exponential distributions, but local sub-exponential distributions, which is the case for the we make the assumption with mu of n equal L of n divided by n to the power 1 plus beta. And I'm not sure if there are other, I mean, do you have examples of offspring distributions which satisfies this, which are not like that? I'm not sure, I don't know. Yeah, so I mean, if you have this, then you get the one.
Here you really want an equality, not.
Yes, equality. So if you put, usually what is well known is if you put stuff like that, and here you only need information on the tail. But when you look at local probabilities, then things become more complicated. It's because it's really the notion of delta sub-exponential distributions with delta equal 0, 1. So this is belongs to Cn plus delta. So delta sub-exponential distributions are defined a bit like that, with Cn plus delta, Cn plus delta. And usually sub-exponential distributions are defined with delta equal to this, which corresponds to being at least equal to. But here we really need this notion. Maybe, maybe there's another way of doing everything without requiring local probabilities, but I'm not sure.
Okay, so there's also a question in the chat that I've been asked to transmit from Rajat Hazra, who says, can the results be pushed to multi-type trees?
Exercise.
Thank you.
Could you tell us about the tricks that you use to do your simulations on which are conditioned on evanescent events? When you simulate your tree, is conditioned to have like exactly n leaves or n vertices? How do you do that?
Yeah, it uses the Luc de Broy's algorithm. Essentially, it's sort of a rejection algorithm where you first have to simulate a bridge. And to simulate a bridge, you say I will first sample the number of leaves I have, then the number of vertices of. You sample to sample a tree with n vertices. You start by sampling the number of leaves, the number of children with one vertex, and so on, with good probabilities. Then you shuffle it to get a degree sequence. The problem is that this is not necessarily the degree sequence of a tree. So you have to satisfy a condition on a sum. So if this condition is not satisfied, you do it again. And if this condition is satisfied, then there is a unique cyclic shift which will give you a degree sequence of a tree. So you can do that if you really want to simulate a tree with size 20,000, or if you want to simulate a big tree, you can just take a random walk and then take some long excursion somewhere and do it a bit by hand.